welcome to this course in noise control and mechanical systems, and in today's lecture we will discuss about noise criteria. I am Professor Sneha Singh from IIT Roorkee. So, we have started with a discussion on what is what are the various principles of noise control engineering, and based on that various kind of noise control strategies. So, basically the source, path, receiver model for noise control, and the various methods within that has been sort of discussed. So, today's lecture we will discuss about because we are trying to control the noise in the environmental noise as a noise control engineer, as well as the noise indoors. So, today's lecture is mostly focused on the noise indoors, as in, so if suppose as a noise control engineer you are given a task that you have to control the noise indoors. So, there should be some reference, how do you say that okay, this particular kind of space, that is the desired noise level in this space, because not every time especially when as a designer and as an architect you are designing these various buildings and various kind of indoor spaces, and where noise control and acoustics becomes a very integral part, then some standards should be there based on which these spaces could be designed. So, that is why we have these various criteria for acoustics of the indoor spaces, and they are specified in terms of the noise criterion curve, noise rating curve, the room criterion curve, and the balanced noise criterion curves, which we are studying today. So, we also call them as the NC curves, NR curves, RC curves, and the NCB curves. Okay. So, these are some standard curves which represent these are the plots or graphs of decibels versus frequency in 1/3 octave usually, and these standard graphs say that okay, this is for this particular kind of space, this could be the typical decibel versus, or this should be the 1/3 octave spectrum variation in the various indoor spaces. So, let us see the very first that is the NC curves or the noise criterion curves. They are a family of standard curves, dV versus 1/3 octave frequency in hertz, and this show that what should be the ideal upper noise limit of a particular indoor environment. So, suppose you say that some indoor environment has an NC value of 50. That means that there are family of curves in this. So, let us say this is the curve belonging to 50, NC 50. So, which means that for that particular space, its 1/3 octave spectrum should be such that it should nowhere exceed this NC 50 curve, like that. So, that is how the definition is, that for a particular environment whatever is the recommended NC value, and you have a standard contour that belongs to that NC value, that nowhere the 1/3 octave spectrum of that particular indoor environment should exceed that level. So, this would be correct if suppose you had 1/3 octave spectrum, something like this, of the indoor environment. So, at some levels, although for most of the ranges the 1/3 octave is below, but at least in this particular region it is above the specified value. So, this is not an acceptable indoor acoustical environment, whereas this black curve becomes an acceptable indoor acoustics environment if suppose this is the recommended value. Okay, this is the recommended one. So, how have they been derived? Usually in the past a lot of research has been conducted, extensive interviews and listening studies have been done with people who are residing in these various kind of indoor spaces, such as offices, public spaces, industrial spaces, and so on. The major concern that was found is that within the indoor space the acoustic should be such that or the noise level should be such that it does not interfere with the tasks that involve listening. For example, it should not interfere with any kind of speech communication, it should not interfere with other listening tasks like watching television, radio, listening to news, etc., music, and all that was a major concern. There were obviously other concerns as well, and the noise spectrum is then measured. So, what happens, suppose you have to find the NC value, you want to find that, okay, this is a particular space, what is its NC value? Then what do? You first measure the noise spectrum of that particular environment or indoor environment or space, and you plot it in the 1/3 octave spectrum, and you compare it with the family of the standard NC curves. This is how the standard NC curves looks like. Okay. So, this corresponds to an NC of 20, this one corresponds to an NC of 30 and so on. So, what it shows from the curve you can overall see is that, because our hearing is more sensitive beyond 500 Hertz and so on. So, there the 1/3 spectrum, ideally this should be the shape of the spectrum within that acoustical environment. So, in this sensitive zones, the dB level should be lower, whereas in the lower frequency zone where a human ear sensitivity is very low, even higher decibel values have been allowed in these curves, and you can notice that these curves are only devised for this frequency region from 63 Hertz to 80 Hertz, and here there was no value, and here also no value. Okay. So, it was one of the earlier curves, and hence this was the frequency region of interest within which these standard NC curves were defined. So, suppose you now have the 1/3 octave spectrum of any indoor environment, you plot it against this particular graph and see that whatever what is the closest NC curve which is just above or equal at all points to that particular octave spectrum, and that will give you the NC rating of that particular environment. So, to illustrate further, let us have a look at a problem and we define the NC rating for an environment. So, let us say we have this NC curves and this red dashed line, this indicates the measured 1/3 octave spectrum. Okay. This is the measured 1/3 octave spectrum of the particular environment of interest, which is here the office space, and we want to give an NC rating to it and say what is the NC rating of this environment, of this office environment. So, we have plotted the 1/3 octave spectrum of this particular space against the standard NC curves, and we want to see which is the closest NC curve, which is where at no point the measured octave levels exceed that NC curve. So, if you see here, let us see, for example, let us solve it. So, if you see here, let us say for example, we start with NC 40 and see whether this is true. So, what you see is that at most of the points, the measured octave spectrum is below the NC 40 curve, it is only within this small region that it is just above it. So, you cannot say it is an NC 40 environment, because at all points the measured octave spectrum of the environment has to be lower than the corresponding value of the corresponding value of that NC curve in that particular octave spectrum. So, if you draw the various, so retaining the shape, if we draw the various NC curves, so we will see that just here as well we will have some NC curve. Okay. This is a curve between 40 and 50, this is an NC 45 curve. So, we have drawn that between 40 and 50 we have that NC 45 curve, which follows the same pattern as the rest of the NC curve and passes at 1000 Hertz from 45 decibels. Okay. So, you join all the plus points here to get that NC curve. So, this becomes your NC 45 curve. So, you see that at NC 40 only for a few values, the octave spectrum of the measured environment is greater than the corresponding NC 40 curve. So, NC is not 40 for this environment. So, just above it is the NC 45 curve. This is the closest curve which is higher or equal to the octave levels and closest to it. We cannot say it is NC 50 or NC 60, they are all above it, but they are not closest. So, the nearest highest curve, that is another way to put it. So, the nearest highest NC curve becomes its NC rating. So, here the office space is assigned NC rating of 45, or simply you can say NC is equal to 45 for the office space. Okay. Then let us see the next curve, which is the noise rating curve. So, just like you have the noise criterion NC curves, which is a standard family of curves which say that okay, this is the typical variation that should be there between the typical sort of graph of dB versus the frequency for the people to have the best experience or the best acoustics within an indoor space. You also have the NR curve, which is again in the similar lines, which, so this was because these are two, they are both doing the same job. Both of these curves are exactly the mechanism and what it means is exactly the same, but their shapes and patterns are different because they have been devised by two separate form of experiments and scientists. So, the NR curves, it was developed again using a lot of studies done with factory workers and also with the people residing near the factories in the adjacent apartments and the houses, and to find what kind of noise level they are finding acceptable. Okay. So, what is the difference between the NR and the NC curve? Then in the NR curve there are also corrections for what time of day the measurement is taken, because NC curve just assumes that at night and at day you have the same kind of, you have the same recommended pattern of noise level, but there they do the corrections with respect to the time of the day, the intermediacy as in the duration of the noise, whether it is a pure tone and all those things. So, various other these factors are taken into account to devise a new set of curves. And what you do, suppose you want to assign the NR rating to an environment, what you do, suppose you say again that some indoor space, it has been recommended, is recommended to not exceed NR, let us say 55. So, what it means is that whatever is the 1/3 octave level in that environment, nowhere it should exceed the value of the, it should exceed the graph of the NR 55. So, this shows the various NR curves. So, nowhere, if suppose this is 50, this is the NR 50 curve, this is the NR 60 curve. So, here we will have an NR 55 curve. So, whatever is the measured 1/3 octave band of that space, okay, nowhere it should never sort of intersect or go above the NR 55 curve at any point. That is what it means, that it should not exceed NR 55. And similarly, just like you have the NC rating, you have the NR rating, what it means is that you find the 1/3 octave spectrum of that environment, you plot it against the family of the NR curves and see which is the closest highest curve where at no point the 1/3 octave spectrum of the environment is exceeding the value, corresponding value of that NR curve, okay, just like how we did for the NC curve. So, let us again see an example. Here also we are given the background octave noise level of a particular office space, a different kind of graph, and okay. So, this is the measured 1/3 octave levels of a space which is an office space, and indoor space is given. You have to find what would be its NR rating. Okay. So, again by the same logic, if you see this is NC 50. So, in most of the cases it is below NC 50, but at some values it is exceeding NC 50. but in most of the cases, but in all the cases this curve is below the NC55 curve. This is the NC55 curve, sorry, NR55, okay. So in all the values, and usually you can also say I am taking these in the steps of 5 dB. So at all the places it is exceeding or it is closest to the NR55 curve, okay. So should we assign it an NR55? Now let us have a look at the previous example. So what happened was that it was just approaching NR45 and I had assigned it a value of NR45. It could also have been very well assigned an NC equals to 44 or something like that as well, which is the closest value. In the same way, so if you have to be more precise, you can say instead of 45, instead of taking the steps of 5, let us say we assign it NC equals to 44, that is the point where this is NC equals to 44 curve, NC as 44 curve. So I think it would be better to assign it a value of 44, which is the closest, where it's exactly the highest level is just touching the NR44 curve, NC44 curve. So here we get the NC as the 44. In the same way here as well, although NC55 is above it, but there should be some curve which is just touching it, tangential to it. So let us find that curve. So over here I think. So again I think it should be NC54 of 53, some value like that. So these divisions are 5. So it is almost 1/3 of the division. So 5 by 3, so close to NC53 I would say. So you can make an educated guess, even if you are not given a family of environments, you can find out which is the nearest curve where it is either below or just touching that curve. So we find that it is just touching at the NR53 curve. Okay, this is the NR53 curve. So here this office space at all points is the office this office space 1/3 octave spectrum at all points is either below or equal to the values in the NR53 curve, and this is the lowest curve to satisfy this condition, because then all the further curves above it will also satisfy this condition. So the lowest curve to satisfy this condition so the office space is assigned an NR rating of 53. Okay. So the lowest curve where this condition gets satisfied, where the measured 1/3 octave spectrum is either less than or just equal to the values in that curve, like that. So you can find out, you can make an educated guess and so on. Okay, so the third criterion, third indoor criterion curves are called as the room criterion curves. These were developed by the scientist Blazier. He had done a lot of hearing studies in the indoor spaces, and especially the indoor spaces where the HVAC machineries were installed. Okay, so it is very specific to an HVAC kind of environment. So they devised a set of curves, and any environment which is an indoor environment with HVAC as one of the major dominant noise sources present in the environment, they must satisfy, or their value should be very closer to the standard RC curves. Okay. So what happens is that in the NC curves, what we saw was that it is one of the most traditional and earliest of the room criterion curves. Okay, the earliest of the indoor criterion curves, and here there was nothing beyond 63 hertz and nothing beyond 8000 hertz. So, in very low and high frequency ranges this curve was not defined. So, in the RC curves they handle this situation So, they also define it for the values which are smaller than 30 hertz, and so here what they have adopted is a more stringent criterion for this, because in the previous curves what is observed is that you sort of have a very lenient criteria on the low frequencies, because the human ear is not sensitive to these low frequencies. So, we are saying that okay, even a much higher decibel level would be okay. So, they are very lenient on these low frequency regions. Okay. Allowed dB levels are much higher compared to what should be there in these mid frequency regions. So, they are very lenient. So, in the RC curve they adopt that no, we should also have more stringent criterion in these frequency ranges, because even at very low frequency ranges what happens is that it is an indoor environment. So, there could be a lot of structural elements within that indoor environment, the walls, roof panels, as well as the various inside panels and structural elements. So, at low frequencies because mostly these structural elements they have their fundamental vibration frequency which is usually at a lower frequency range. So, suppose sound is there at these low frequency range, even if the ear is not very sensitive, but this can lead to the vibration of the structural elements within the room, and because of that the room becomes susceptible to structural damage and that. So, it is again even at lower frequencies having a very high level is not desirable, because it will induce the vibration of the structural elements and essentially the damage and the wear and tear of the elements in the room, and hence these stringent criteria are there. And here any space is assigned an RC rating not by the logic of what we were using for NC and NR curve, but rather what we do is we plot the 1/3 octave spectrum of that environment and see what is the arithmetic average of the measured 1/3 octave spectrum at 500, 1000 and 2000 hertz, and that average becomes its RC rating. So, this shows the RC rating. Here more stringent criteria is available here, rather than the curve going very exponentially in the higher direction. We have flat curves, because even these conditions are not desirable, because this can vibration induction will, this can induce vibration. Although we may not hear these sounds very loudly, but vibrations can be induced in the room's structural elements, and these can get damaged. So, even that is not desirable from the vibration point of view, and hence more flatter and downward compared to the previous curves we have the downward values. Okay. And for this curve the typical slope is 5 dB per octave. It is a more flatter curve we are observing here. So, let us say for example, this is the RC curve and the background octave levels of an HVAC plant, because the RC curves were usually designed for HVAC machineries, and although it is applicable for other indoor spaces as well, but it works the best when you have the noise source as some kind of HVAC machinery. So, it is sort of, so we have measured the in an HVAC plant we have measured the background octave levels, and that is plotted as this line. So, this is the measured 1/3 octave levels of an indoor space. Okay. So, you have to find what is its RC rating. So, here you do not see what is the nearest curve. So, here if you go by that logic, okay, that the nearest RC curve is 50, where it is just above or equal to the so by that logic RC should be 50, but that is not the logic that is used in case of RC rating. RC rating is simply whatever is your measured octave levels, you do the arithmetic average in the 500, 1000 and the 2000 hertz range. So, the RC rating would of this particular measured space should be, let us find out what is its 1/3 octave values at 500, 1000 and 2000 hertz. At 500 we have close to 47 dB, at 1000 and 2000 hertz, these are similar values which is close to 42 decibels. So, we do an arithmetic average of its value at the 3 kind of points. So, whatever is the measured 1/3, so you do not have to bother with what is the standard RC curve. You simply have the 1/3 octave spectrum, find out the average values in the 500, 1000 and the 2000 hertz range, and that becomes your RC rating. Okay. So, this particular, so measured HVAC plant gets an RC rating of 44 dB or simply 44. You do not even need to mention dB, automatically it is taken as a dB. Okay, so the last kind of curves you will be studying is the balanced noise criterion curves. So, they were an improvement on the already existing noise criterion curves. So, here what happened is that again similar to the noise criterion curves, but now what they did was that they sort of incorporated more stringent criterion in these lower frequency ranges, okay, and they lowered the slope of decrease in the decibel levels per octave. So, instead of having a curve like this, they had a curve more like, you know, more flatter curve compared to that. So, some kind of balancing was done to get the new balanced noise criterion curves, which is one of the latest curves, and the NCB rating of any environment is simply you, again just like in the RC rating, you do not need to know what is the NCB standard NCB curves of an environment. You simply measure the 1/3 octave levels and find out what is the average value in the, what is the arithmetic average of its 1/3 octave value at 500, 1000, 2000 and 4000 hertz, and you will get the NCB rating. So, this is the typical NCB curves which shows the standard or simply the recommended. So, these are just recommended patterns. That does not mean that the indoor space will actually have that kind of pattern. This is just recommended because this has been found to be giving the best kind of experience to people indoors, that the pattern should be, the shape should be like this, that per increase in the octave it is reducing by 3.33 decibels. Okay. So, that is just a recommended shape of 1/3 octave spectrum of a space. It is just a recommended that you will get the best acoustics if your 1/3 octave spectrum is supposed to follow this kind of a shape, but it need not do in the reality, but this is just something that is recommended where it gives the best results. And again more so and in these regions have been flagged, which means that although acoustically it is fine, it is dangerous because vibrations happen which hamper the various elements within the roof. So, this is a danger zone. Okay. So, let us see, this is a family of the NCB curves and the octave levels of an HVAC installed within a large room, and the the noise levels in that large room is measured, and this is the measured 1/3 octave. So, over here we represented in the octave levels. Okay. So, I think even in this one we had the octave levels, not the 1/3 octave levels. This is something which I would like to rectify. These are measured octave levels. Okay. Okay. In the same way, everywhere this is measured in the octave spectrum, not 1/3 octave spectrum. Okay. Okay. So, this is octave spectrum. All the curves are measured in octaves, not in 1/3 octaves. So, everywhere it should be octave levels. Okay. So, they are measured in the octave levels. So, now let us see our problem at hand. This is this is the measured NCB, the measured octave levels of an indoor environment. Okay. And you have to find its NCB rating. So, again you do not need to bother with what looks like, how and where it is touching the NCB curves, okay, which is the curve that is just below or just above, nothing like that. Simply find out what are the octave levels in the 500 hertz, 1000 hertz, okay, 2000 and 4000 hertz range, and do their arithmetic average. So, at 500 it is having a decibel levels of close to, I think it is 44 dB. At 1000 it is having a decibel level close to 41, yes, and 2000 it is having a decibel level close to 37, and at 4000 this is having close to 31. So, these values you find out, do their arithmetic average, and you get the NCB rating of this environment. So, this becomes the NCB rating of the measured space. Okay. It's simply 38. You can write decibels or you can just omit decibels, both of them mean the same. So, so I would like to close this lecture with a quick discussion and a table that gives you, some of the recommended NCB ratings. Acousticians, they recommend that this should be the typical NCB rating of an environment. So, for example, you have a broadcast or recording studios there, because you are recording, sensitive sounds, so in the recording you want to ensure that, you have least noise. So, very high signal to noise ratio, and hence you need the lowest NCB rating of 10 in various concert halls, opera house and recital halls. In the absence of any listener or in the absence of any additional source, just within that space, the recommended NCB rating is 10 to 15. For the large auditoriums, if it is a smaller room, then you need a lower rating. For a larger room, you can still go away with slightly higher rating. So, in these large spaces, you have less than 20, then smaller auditoriums, theatres, musical rooms, meetings and conference rooms, this is the recommended NCB rating. Then the bedrooms, sleeping quarters, hospitals, residences, apartments, hotels and motels. Followed by that, you have these private or semi-private offices. So, I am going from lowest to highest recommended NCB ratings. So, there you can, in these office spaces, conference rooms, classrooms and the libraries, you can have a typically 30 to 40 dB as the NCB rating. Then for the living rooms and the drawing rooms in the various houses and buildings, you can have again 30 to 40. So, this is, these NCB ratings are, in absence of any source, which means that if there is no source, obviously somebody starts talking, it will not be 30 to 40. So, just in the absence of any source within that space, so in absence of any source within the space, this should be the recommended rating. So, this is like the lowest possible background environment or the background noise level. Then for larger offices, reception areas, retail shops and stores, cafeterias and restaurants, the minimum NCB, the recommended NCB rating or the minimum noise level should be closer to 35 to 45. Then lobbies, laboratory, workspaces, engineering rooms, general secretarial areas, slightly higher, 40 to 50 NCB ratings have been recommended. Then we have larger maintenance shops, industrial plant control rooms, offices and the computer equipment rooms, kitchens and the laundry areas, where in general, typically you have louder things going on. So, in the absence of any direct activity going on in that space, the typical NCB rating could be 45 to 55. Then in the shops, garages, etc., 50 to 60. Workspaces, where speech and telephone communication is not required, you can have slightly higher, and so on. So, thank you for listening.